Dear learners, welcome to our week 2 lecture 4. In this lecture, I will explain the development of cell governing equations. Already we have covered the basic assumptions in the last lecture, that for Law's first approximation theory or Love-Kirchhoff shell theory, and then the first order shear deformation theory where shear strains are not neglected. So, our very first step for developing governing equation, basically displacement based governing means formulation, that first of all we have to choose a suitable displacement field. So, for the present case, this displacement field is finalized. In the last lecture, I have explained that how to obtain this expression for case of Love-Kirchhoff shell by putting gamma 1 3 and gamma 2 3 equate to 0 and integrating with respect to zeta coordinates. But for FSDT theory, our u1 0, u2 0, w naught, psi 1 and psi 2 are primary variables, where psi 1 and psi 2 basically unknown rotations, and u1 0, u2 0 cause a membrane stretching effect, and w naught is transverse displacement. Next step is to choose a suitable strain displacement field. In the course, we are going to discuss about buckling of shell also. For that purpose, we need to consider geometrical nonlinearity, so that at the end of the day that we can use the governing equations. If we start with the linear one, then we will not have the sufficient number of terms to go for buckling cases. So, here already in lecture 2 that complete strain displacement relations were having linear and non-linear term were given, and out of that we said that when we talk about von Karman nonlinearity, in that nonlinearity effect is considered through the deflection u3, that variation means u3 differentiation with respect to alpha and beta taken care, and the higher order terms are neglected, which is related to u1 and u2 and the mixed one also. So, we will going to have the nonlinear terms in epsilon 1 1, epsilon 2 2 and epsilon 3 3. These three terms are extra when we consider the von Karman nonlinearity. Other than that, all these are our linear terms. So, this is our strain displacement relations. Now, we have to rewrite these strains considering this displacement fields. We have taken displacement field like this. So, substituting the u1 like this, u2 like this, u3 like this. So, this will be modified and will look like this. So, basically the whole strain components are arranged in this form. Let us say if it is epsilon 1 1, it will be arranged in this form epsilon 1 1 naught plus zeta times of epsilon 1 1 1. So, whereas this cause stretching effect in the shell, whereas this will cause bending effect in the shell. Sometimes we call, in some of the books it is also denoted by kappa like this, K11, K12. So, related to curvature terms or the bending. Here in epsilon 1 1 0, the explicit expression, this terms will be 0, u1 0 alpha with respect to derivative u2 0 d1. So, basically this comes from linear one, and this is the contribution due to non-linear one, and this epsilon 1 1 1 is contribution due to the bending effect, because psi 1 and psi 2 are our rotations. If you take derivatives along that, they will cause a bending effect. Then epsilon 2 2 we can write like this. So, it is a simple substitution, and wherever required we will do some derivatives or writing in more simplified manner, means arranging the terms, because ultimately when you have a u is equal to u10 plus zeta times of psi 1. So, these terms will contribute to the curvature, these terms contribute to the stretching. So, same way we have arranged like this. The main difference is here that gamma 1 2 in previous expression, gamma 1 2 is written in journal form, where d by d alpha u2 by a2. So, we have simplified it, again this has been simplified it, and then substitute the value of u1 and u2. So, this gives you slightly big expression where 1 by a1 linear terms and this contribution. Here it will be 1 by a2 and 1 by 2 a1 a2. So, basically there are some terms in which 1 by a1 can be taken out, and there are some terms in which 1 by a2 can be taken out. So, these terms corresponding to the linear contribution and these terms corresponding to the non-linear contribution. Then gamma 1 2 can be expressed like this. Gamma 1 3 naught, in the gamma 1 3 and 2 3 there will be no curvature terms. So, only in plane stretching terms are written like this. Now, we have to come out that definition of stress resultants. So, we have to define the stress resultants. So, there are number of ways to define stress resultant for the case of cell. So, if you go through a book like book by Harry Karus, there the stress resultant is defined like this, that they are defined per unit of arc length on the reference surface. So, basically at the reference surface the curve length is slightly different, and at let us say zeta height, that is something different. So, if this is our reference surface, this is our alpha coordinate, beta coordinate. So, line will be this line, over this line alpha will be constant, over this line beta will be constant, and curve length is ds2 and this curve length is ds1. I would like to say that what is ds1? ds1 is basically a1 1 plus zeta by r1 into d alpha. Basically this is your d alpha, and ds2 is equal to a2 1 plus zeta by r2 d beta. So, that over this phase, if we are talking about this phase, let us say stress component sigma 1 1 is acting over this phase. So, I have shown it here. So, it is coming. So, we want to know the resultant. So, integrating over the thickness with this zeta coordinate. So, total force will be sigma 1 1 into that area. That area is ds2 and d zeta divided by arc length on the reference surface. So, arc length on the reference surface will be ds2, where zeta is 0. Basically at the reference surface zeta is 0. If you put zeta is 0, so only a2 and d beta will come up. So, we will write sigma 1 1 ds2 is a2 1 plus zeta by r2 d beta and d zeta, and ds2 0 a2 by d beta. So, they will get cancelled out. So, n1 can be defined at sigma 1 1 1 plus zeta by r2 and d zeta. Same way we can define the moment 1 1, that zeta sigma 1 1 zeta times 1 plus zeta by r2 into d zeta. Then n12 on this surface. So n12 again can be defined zeta sigma 12 or tau 12, whatever you want to say, that zeta by r2 and d zeta. Now we are talking about definition here. So the normal component is this. So basically sigma 2 2. So if you want to define the stress resultant along this coordinate, it will be n2 2 definition will be zeta coordinate sigma 2 2 ds1, length is along ds1, and d zeta, total force upon me ds1 of 0. So from there we can find out that ds1 is a1 1 plus zeta by r1, and that becomes sigma 2 to 1 plus zeta by r1 into g zeta, integration over zeta. So I would like to point it out here that for n11 here 1 by zeta by r2 comes, that radius of curvature in second direction, and then radius in first direction. So they are interchanged. It is point to be noted that most of the time sometimes we ask that define the stress resultant for the case of cell, identify the coordinates properly. So students may do mistake that near the n11 they used to write r1, or instead in n22 they used to write r2. So one has to be careful that when you are defining this, it will be the second direction radius and this will be the first direction radius if you define the coordinate system like this. In the second book which I have taken that some of the basic equations like J. N. Reddy, Theory of Plate and Shell. In that or some older books of also that based on shell theories, it is given that let us, it is also saying that the physics point of sense that tensile force measured per unit length along beta coordinate line on a cross section perpendicular to alpha coordinate can be represented like that force will be sigma 11 into ds2, where this line alpha is going to be constant. So total force on a differential element can be written as minus h by 2 to plus h by 2. Yes, we have taken the shell element thickness is minus h by 2 to plus h by 2 and total force will be into integrating over that. So if you substitute the value of ds2, we know that a2 is not a function of zeta, it is only a function of alpha and beta. So we can write like this. So if we compare this thing that what is, let us say a normal resultant force is acting as in plane stress resultant n11. So our total will be, over this reference surface will be a2 and d beta total force. So if we compare with this, we see that a2 and d beta is here. So n11 by definition comes like this, that minus h by 2 to plus h by 2 sigma 11 1 plus zeta by r2. So you do anyway that both of the results are same, only that in this we are comparing that n11 with the help of stress resultant, and previously we directly or mathematically defined that if we take stress resultant per unit length of reference surface, arc length of reference surface, then we can define it. So already I have discussed that how to obtain n22. Now we are talking about a third component, tau 13 and tau 23. So I have written here sigma 13. So sigma 13 1 plus zeta by r2 will be designated as q1. Then q2 will be designated as sigma 23 1 plus zeta by r1 d zeta. Here point to be noted that for definition of n12 contains sigma 12 1 plus zeta by r2 d zeta. n21 definition is sigma 21 1 plus zeta by r1. You may say that tau sigma 12 equal to sigma 21, or you can say that tau 12 equal to tau 21. But N12 not equal to N21. Here the R2 and R1 are different. So, for the case of spherical cell they will be same, and for the case of plate, because R1 and R2 both are infinity, in that case it will be same, but for other cases if you talk about a cylinder, then they will not be same, because in one direction it is infinity and in another direction it is R. And you take another some conical shell or any other type of shell where R1 and R2 are not equal, then N1 not equal to N2. Same way we can define the couples, that moment in one direction. So, zeta times of sigma 11 gives you the moment in one direction, and M12 sigma 12 in zeta times. Same way M22 can be defined like this. Here again moment in 1-2 direction cannot be equal to moment in 2-1 direction. So, this type of expression you come to know only when you are going to drive equations for a shell. If you have done about till plate only, you will not think that okay this may be different, or if you see that the stress resultant can be special case, like if you put R2 for a case of a plate. So, for a case of a plate it will becomes like minus h by 2 to plus h by 2 sigma 11 and dz. So, that is the definition for a stress resultant for the case of plate. Over this surface element, reference, remember that N11, N12, N22, N21, M11, M12, M21, M22 and Q1 and Q2 is shown here. So, this is very important part, we are going to use these definitions, and point to remember is that for case of N11 it will be 1 plus zeta by R2, for case of second direction it will be 1 plus zeta by R1. Now, in the third step we have to derive the governing equations based on the Sanders cell theory and considering the von-Karman nonlinearity. So, now following the Hamilton principle, it states that integration from 0 to t, that del k means sum of total energy and dt is going to be 0. So, what is that total energy? That first variation in kinetic energy minus internal work done, or sometimes you called it strain energy, elastic strain energy. It is elastic strain energy, but it is very convenient or generalized to say internal work done, because later on if somebody want to study a piezoelectric shell or some functionally graded shell made of some other different material. So, instead of a elastic they may have some electrical energy and some other form of energy. So, they will be also clubbed together here under the term of internal work done. Then the external work done. So, over the surfaces the work done by the traction forces, that may be the loading or the traction forces. So, we will find out the external work done from there. So, that is going to be 0. So, first we will calculate what is the kinetic energy for the case of a shell element. So, for a continuous body the kinetic energy expression can be written as half rho ui dot square dV integration over volume. So, for a continuous body the kinetic energy is expressed like this, where u is displacement, u dot means du by dt. So, it is a standard expression that whenever you have a time derivative you take derivative with respect to dot, and whenever you have a space derivative then you put a comma alpha or comma beta like that, or comma zeta, so on. So, we have a time derivative, basically you can say that half mv square for a discrete system like a car of a mass m moving with the velocity v. What will be the kinetic energy? Then we can say that it will be half mv square. But same way if a beam of a plate or some or a shell is vibrating or it is having some kind of motion, then it will be half rho ui dot square del v. Then we have to take first variation, then already I think I assume that you be aware about that how to take variations in that quantity, but I would like to say that del is a variational operator and it is behaving like same as our differential operator. So, if we want to take first variation in this, so we will say that twice second term same and variation in the that quantity. For example, you want to say y is equal to x square. So, what is that dy by dx? It will be just twice of x like that, and then you say that del of x. So, same way we have written that. So, 2 will get cancelled out and ultimately the expression will look like rho u dot I del u dot I dv. So, this is our expression of kinetic energy, first variation of kinetic energy in the index form. Now, we have to write in the explicit form del k. So, ui means u10 or u1 I coming twice, it means summation over I. So, u1 plus u2 plus u3. So, u10 zeta times psi1 dot plus multiply variation in that del u10 dot plus zeta times del psi1 plus second term u20 plus zeta times psi2 dot multiply del u20 plus zeta times del psi2 dot plus the third term w dot into del w naught and the volume. Now, you know that volume dV is ds1 ds2 d zeta and ds1 is a1 1 plus zeta by r1, a2 1 plus zeta by r2 d alpha d beta and d zeta. So, we have to now if we multiply these terms and mathematically simplify. So, there will be some terms in which there will be no zeta like u10 and del u10, u20, del u20, w naught. So, they will be kept together and there are terms where zeta comes, we can say common out and psi1 and then again u10, those terms contains together and there are some terms where zeta square. So, these terms comes together. Now, we see that these terms a1 1 plus zeta by r1, a2 1 plus zeta by r2. So, we have to now there is a time to define the moment of inertia. So, that I0 will be defined at rho times 1 plus zeta by r1, 1 plus zeta by r2 d zeta minus h by 2 to plus h by 2. This is the definition of moment of inertia resultant for the case of doubly curved shell. So, you see that this expression is entirely different. If you talk about for the case of a plate, it will be rho into dz minus h by 2 to plus h by 2. So, if you put r2 infinity here r1 infinity, this expression becomes this expression. Then I1 is defined rho times zeta times rho, same expression, then I2 is defined rho zeta square and the expression like this. So, by defining this moment of inertia resultant, we are converting a volume integral to a area integral. So, I would like to say that this is the essential step in any two dimensional theory, whether you are interested for a shell or a plate or a beam, then you need to follow this step. Without defining the inertia resultants or stress resultants or moment resultants, you cannot convert a volume integral into a area integral. So, by following this procedure, this becomes a area omega I naught and coefficient of this, I2 coefficient of this and I1 coefficient of this, and here A1, A2, d alpha 1 and d beta 2. Okay. Here the term like this, del u0 10 dot, del u20 dot, w20 dot. So we have to get rid of this. Why we want to get rid of this? We do not want any derivative in the variation. So we have to remove these things. The reason behind that, let us say if I explain the first variation in the case of time, that let us say time t is equal to 0 and time t is equal to f, and a function f t is given. So let us say a point that when time t is equal to 0 and time t is equal to f. So the exact solution can be expressed by this black line, and we are taking first variation because we are assuming that let us say some variation of from, because we do not know the exact solution. So we are taking a arbitrary variation in that function and going to minimize this. So it is delta f, that is first variation, and at the boundary this term is going to be 0. So we have assumed a virtual variation in a quantity f, but we do not have any information about the del f del by del t, its time derivative we do not have any information. So we want to convert it to its basic form. So we do not want that wherever you have a variation terms, either it is a time derivative or it may have space derivative, we have to get rid of this. So in the very first I am explaining with the help of first term, then same way the other terms can be converted. Let us say, can we write this term u1 dot u10 dot del u10 whole derivative with respect to time. So differentiation of this term with respect to time, second term as it is plus first term as it is, differentiation of second term. This is the simple rule of a differentiation when you have a two function u and v. Let us say you want to do a differentiation with respect to time. What do? You say that differentiation of first, second as it is plus first as it is, differentiation of second. So by following the same we have obtained. Now you see that this is our term which is we want to know. So you can express this thing that u1 dot del u dot whole derivative with respect to time minus this term u1 double dot. Now it is becomes a acceleration term, check in time derivative, then del u10. So if we substitute in this equation and also take the time integration and like this. So you see that if there is a time derivative and integration over time, so we can integrate with respect to time, and from using this term we do not get any advantage. So we will keep it same on the same integration time and area integration. But if you do integrate with respect to time and take the limit 0 to t, at the initial time and final time the variation is 0. So this term will not contribute. My purpose is to say you that this term will give only one contribution, that minus of u10 double dot del u10. So we will get one contribution, the other time derivative is going to be 0. So by following the same procedure, that first variation in kinetic energy, all the terms are written like this, u1 double dot, u2 double dot, w double dot, and then the coefficients of I2, then coefficients of I1 and A1, A2, A. So with this it is the perfect terms, these can be directly go to the governing equation. So we define that equation number A, because we have to also calculate the internal work done, external work done, and then later on we are clubbing together. So I am going to write that equation A, and then from the internal work done del Wi. What is the internal work done for the case of elastic body? It will be integration over volume sigma 11 del epsilon 11 plus sigma 22 del epsilon 22 plus tau 23 del gamma 23 plus tau 13 del gamma 13 plus tau 12 del gamma 12 and volume small a11 plus zeta by r1. So हम इसको बोल सकते हैं this is a1 and we can call it this is a2 d alpha and d beta d zeta. So we have to write this variation form of strains. So we know epsilon 11 is this epsilon 110 plus zeta times del epsilon 11. So if we take the first variation, it will be just putting del epsilon 11 del epsilon 110 zeta times del epsilon 11. Similarly, del epsilon 22 del gamma 12 del gamma 13 and del gamma 23 and substituting in this equation. Now working with this equation, all these things together will be very lengthy. So we will work one by one. Let us say sigma 11 and del epsilon 110 plus zeta time del epsilon 11 can be taken as I1 and then sigma 22, let us say integration I2. We are just dividing the like small integration, later on we are club it together I3, I4, I5. So we are talking about a first integration. Sigma 11 del epsilon 11 zeta times del epsilon 111 a1 1 plus zeta by r1 a2 1 plus zeta by r2 d alpha d beta. Now we need the explicit expression of epsilon 11 and epsilon 111. So I have written the explicit expression of epsilon 110 and if we take the variation, so del will come here and again del will come here and so on. So we have to do it carefully that sigma 11 1 by a1 common and taking the variation del u10 comma alpha, because if we write in that del by del alpha, it takes huge space and working with that is slightly difficult. So I have written a small form. We can write del u10 comma alpha and del u20 by a2 a1 comma beta and del w naught a1 by r1. So this is our linear contribution. Then non-linear one. So non-linear, you see here is a square. So twice will come here. So 2 and 2 will get cancelled out. So it will be just 1 by a1 is here. It will be basically a2. It should be a2. So a1 a2. So it will be w comma alpha minus a1 u10 and their variation plus zeta times 1 by a1 psi 1 comma alpha plus del psi 2 a2 a1 comma beta and a1 a2 d alpha d beta. Now you see that 1 by a1 is outside here, 1 by a1 a2 is outside from the nonlinear terms and 1 by a1 is outside from the curvature terms and here is a1 a2 a3. So a1 get cancelled out, so it becomes a2 come up here, here nothing, again a2 come up here. So a2 contains small a2 1 plus zeta by r2. So it will go into the definition of n11. n11 का definition क्या है? n11 is nothing but minus h by 2 2 plus h by 2 sigma 11 1 plus zeta by r2 into d zeta. So that part go into the definition and small a2. So now we can say that this term with this becomes capital N11 a2 and this terms remain same. Here a1 a2 both get cancelled out. So a new constant is defined n tilde nn, which is nothing but it is just sigma 1 1 into d zeta. They will get cancelled out. Later on we can multiply and do something. And then zeta times. So, it will go to the definition of a moment m11, a2 and red terms together. Again you see here del u10 comma alpha. We have only information about del u10. That okay, we have taken variation in primary displacement del u10. We do not have any information about its space derivative with respect to alpha. So, we have to reduce it to del u10. So, by following the same technique which we have followed for the case of time derivative, same way let us say we can write n11 a2 del u10. Here we have to consider n11 and a2 is one variable. So, differentiation of that function and it you say that del u10 plus n11 a2 del u10 comma alpha. So, this is the same term. So, we will put it here and whole derivative with respect to alpha minus n11 a2 comma alpha. So, this term will give you two terms. One will go to the boundary, that whole derivative with respect to alpha, and other term will remain on the area. Same way here we need not to do anything and here also we do not do anything because there is no derivative, but here is the derivative in the nonlinear term in the first term and derivative in the moment term. So, two term here, two term here and two term here. So, first two terms and then second as it is, then third as it is, then the moment gives these two terms and m11 alpha beta. Same way the nonlinear terms. So, again this whole will be treated as a one term. I am circling. So, whole derivative comma x, that we have to consider as a single term, then only we can get rid of their derivatives. And the second term again it is the d alpha and d beta. So, in this way this is the expression required for differential equation and I1 now I am denoting as a equation B. Now, come to the I2 expression sigma 2 2. So, it will be del epsilon 2 2 0 plus zeta time del epsilon 2 2 of 1 a1 a2 d alpha d beta d zeta. So, we have to substitute the expression of del epsilon 2 2 0 and del epsilon 2 2 1. So, the expression is again here is some mistake is there. So, in the nonlinear term specifically. So, epsilon 2 2 expression is put it here. Okay, I will explain. Yes, it may be a2, a1, that in the next lecture I will explain the nonlinear terms, the exact terms of the nonlinears. So, linear one is right and the curvature is right, only the nonlinear terms I have to take care. So, I will explain in the next lecture that what will be the exact contribution of the nonlinear terms. There is some issue. So, we can write that del u so on and del of nonlinear terms and epsilon 1 1 terms. Again using the concept of in plane stress resultant, sigma 2 2 gives you n 2 2 and zeta times of sigma 2 2 gives you m 2 2. Same way here is a derivative with respect to beta, we want to get rid of that and we can again with the help of using the basic concept that n 2 2 a1 del u 2 whole derivative beta can be written as n22 a1 whole derivative beta del u2 0 plus n22 a1 del 2 0 comma beta. So, from there n22 a1 del u2 0 comma beta can be written as this term. So, this I2 expression will be n22 a1 del u2 0 comma beta minus n22 a1 plus a1 will get cancelled out. So, a2 comma alpha del ug1 plus n22 a1 a2 upon me r2 plus n22 hat w comma b minus a2 by r2 u2 0 del w naught derivative with respect to beta minus n22 hat w comma beta minus a2 by r2 u2 0 whole derivative beta and del w naught. Again other terms remain same. And from the moment 1 m22 a1 del psi 2 whole derivative beta minus m22 a1 derivative beta del psi 2 plus m22 a1 get cancelled out del psi 1 and a2 comma alpha. So, in this way this is our expression number C. So, in the next week lecture I will explain I3, I4 and I5 and external work done, and also come up with there is some issue in this definition of nonlinear terms. I will clarify that. Thank you very much.